Okay, now we're moving on to sequences. And remember, sequences are just a series of sequence of numbers. Sequence is different than series, right? So sequence of numbers, and we're going to be asked if it converges or diverges. And if it converges, they'll want me to find out where it converges to. Where it converges to. Okay. In general, you take a limit as n goes to infinity of the a sub n. And if it equals a number, it converges to that number. If the limit as n goes to infinity of that thing is dne or infinity, then I can say it diverges. So that's the in general cases, right? Okay, so let's just do some examples. Just want to make sure that you're thinking about, so let's do some trig guys first. So there's arctangent of 2 over n, and then here's another arctangent. Oh, sorry, I said that wrong. So n over 2, 2 over n, and let's do cosine of 2 over n, and cosine of n over 2. Okay, so this would be the instructions, converge or diverge. So you look at these and you think, oh yeah, I'm supposed to take a limit. If I take a limit as n goes to infinity, so you need to write the limit out, right? You don't write the infinity in there, you think it. So put the infinity in, and that gives me infinity over 2, which is infinity. Arctangent of infinity is pi over 2. So that means it converges, it goes to a number. If I do this one, take the limit as n goes to infinity, really similar. But you have to look to see what the infinity does on the inside first. So 2 over infinity gives me 0. Arctangent of 0 is 0, so it converges, but to a different number. A trig function, sometimes you use squeeze theorem with cosines or sines, but always check out to see what's happening when you plug in infinity. So if I plug in infinity, I get 2 over infinity, which is 0. Cosine of 0 is 1, so it converges to 1. If I take the limit as n goes to infinity of cosine of n over 2, infinity over 2, that gives me infinity. Cosine of infinity, that does not exist because cosine just kind of keeps going between 1 and negative 1, so the answer is not infinity, but the limit does not exist, and as a result, I can say that this diverges. Okay, so that's some trig things, and then you know that if you had like a cosine of n over 2 to the n, or if you had sine squared of n over n squared, if you try to take the limit of this, you get dne over infinity. That's a dead end. That tells you to use squeeze theorem, right? So then you start off with cosine of n is between 1 and negative 1. Then you divide everywhere by 2 to the n. And then you show, right, you have to write this out for me. You show that the limit of each of the not negative, the other one, 1 over 2 to the n, that they go to the same thing, right? The limit of this and the limit of this. So then you can say, therefore, and you just want to rewrite the sequence, right? This thing converges to 0, and then just say by squeeze theorem. Same thing with this one. If you start to take a limit, and you don't have to show this step, but if you start to take a limit and then you recognize, oh yeah, I've got dne over infinity, dead end. So that's the time to use squeeze theorem. So whether it's always going to be a sine or a cosine when you're doing squeeze theorem, if the trig function is squared, then it's bounded between 0 and 1, and then I divide everywhere by n squared, right? So this just is 0. So the limit as n goes to infinity of 0, that's 0. Pretty silly to have to write that. And then 1 over n squared, 1 over infinity squared, that's 0. So then you can conclude this converges to 0 by squeeze theorem. All right, so let's do just a couple more. So what if you got something like this? So 2n plus 1 cubed over 4n cubed plus n. So you start to think, okay, in general, I take a limit, right? So 2n plus 1 cubed over 4n cubed plus n. So I'm looking at just exponents here. I'm going to go do highest powers. So if I was to pull out the highest powered term with its coefficient, here I would get 8n cubed. I am not ever going to ask you to multiply a cube out. You're just looking for the highest power. And here I'd have 4n cubed. So this is infinity over infinity, which is more work. But you know you cancel. So I cancel those. Oh, and I'm just left with 2. So it converges. So it's not necessary to use L'Hopital's rule every time you get infinity over infinity. Highest powers really can be useful. Okay, so that's a case where you would want to use highest powers. What if you had something like ln of n squared over n? So you start, in general, you take a limit, ln of n squared over n. I do get infinity over infinity. I cannot do highest powers. This is the time to change it to x's as you're doing L'Hopital's. So 2 ln of x to the 1 power times the derivative of ln of x, which is 1 over x, over 1. All right, so I'm just going to rewrite it so you can truly see it. So I have 2 ln of x over x. So this is still infinity over infinity. Let's do L'Hopital one more time. So 2 times 1 over x over 1. So now if I put it in infinity, I get 1 over infinity, which is 0. So it converges. All right, so what if I had another one with an ln? So limit as n goes to infinity, n over ln of n squared. Before I would go do anything, I would rewrite this, right? This 2 here can come down in the front. So now this is infinity over infinity. So then I would take the derivative, changing it to x's. So I get 1 over 2 times 1 over x. So that x flips up to the numerator. So I get x over 2. The 2 stays down there. And then infinity over 2, that's infinity. So it diverges. So changing it to x's if you have to use L'Hopital's rule. Okay, so that's in general. And if you can just use highest powers, that's a great thing to do too. So then I'm going to stop here.